Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, I guess we can start. So it's my pleasure to have George visiting us today. I'm sure many of you know George from his column on the ACM, communication of the ACM, called Vicious. And of course, you also know from his involvement with the FreeBSD community, where he's been very active, both from a development and a research perspective, as well as teaching perspective. And in fact, he's here in Cambridge because he's designing a new master course for operating system at the computer lab. And today he's going to talk us about FreeBSD and how they've been using it as a research platform. George, over to you.
Thank you. Good afternoon. Yep, my name is George Neville-Neal, and I'll be talking about systems science and FreeBSD. So what is FreeBSD? I find it a bit amusing to be given a talk on an open source operating system in this particular venue. But it should be good fun. So FreeBSD is a complete integrated Unix system. What we mean by complete is when you get it, you don't have to install new packages to develop software on it. The original goal of all of the BSDs, including FreeBSD, is that when you get this one thing, you can actually start doing work immediately, and you don't have to start adding stuff to it. Modern multiprocessing, multi-threaded preemptive kernel works beautifully on SMP hardware. Unix, POSIX, BSD programming interfaces, which are familiar to people. Which are very familiar to people from long usage. Extensible debugging tools, both for userland and kernel debugger, userland debugger, and a number of tools that I'll actually talk about later in the talk. Multi-protocol network stack, so one of the things that the BSDs and FreeBSD have had for a long time, and one of the things that a great deal of research is done on is on network protocols. So it's very important that we have the ability to add new protocols, not just the ones that you see on the open internet, but new protocols that get used in terms of research. Unified coherent build system across components. We can build natively or cross-build so that we can do embedded research as well as research on sort of more common server architectures. Extensive documentation. One of the things that Paolo mentioned is that I not only work on the code, but I also work on the text. FreeBSD is an incredibly well-documented system. In a month, there will be a second book about the kernel, which is my second book, co-authored with Robert Watson at the University of Cambridge and Kirk McKusick, who's been working on BSD for quite a long time. So it's not just a kernel and it's not just a user space. It's also a huge family of ports and packages, everything from systems like Zookeeper or editors or other compilers or whatever tools people need to do their work. Those exist as what we call third-party software ports, and those have all been adapted to run on top of the operating system. So it's this entire package of the kernel, the user space utilities, documentation, and then all of the third-party tools you need to do work. Who uses FreeBSD? Quite a number of people, it turns out. Some of them seemingly pop up out of nowhere. Some of them we know pretty well. Apple, Yahoo, WhatsApp, which is pretty amusing at the moment given what Facebook paid for them. Netflix, Juniper, there's a whole list here. FreeBSD exists in gaming systems like the PS4, filtering systems from Cisco and Norse, storage systems from EMC, which is formerly Isilon, HP, and NetApp. So it's used in a lot of places. And why that's important is, while you probably are really interested in how you use the system to do research, a lot of people really like their research to be applied. So one of the nice things is that things that get researched in FreeBSD eventually wind up in products and eventually wind up in the real world. And that's a really nice story to be able to tell about tech transfer from research to industry. So FreeBSD is not just a collection of source code that exists on a bunch of servers, it's a project. And it's a project that's carried out by a large number of people worldwide. The project itself breaks down into several different groups, all of which whom work together to produce the system. We have what are called source committers. These are the people you would think of as committing to the kernel code or to userland utilities. There's 300 of those people who have access to the central repo and can update the kernel on an ongoing basis prior to release. the ports, when you have 24,000 ports, you can't support that with a small number of people. So there are a large number of people in the world who all they do is maintain a few ports that are shipped with FreeBSD as part of the ports collection. So there are several hundred of these people. Some of them will work on 1 or 2 ports. Some very adventurous people will work on 20 or 30 ports. I can't even imagine maintaining 20 or 30 ports myself. That sounds like a lot of work. Large independent documentation team. You don't get great documentation out of developers. You're supposed to laugh at that joke. Sometimes you do, but not often. So one of the things that FreeBSD and the BSDs have always had is a commitment to a really good documentation so that people can use the system. We've always produced books and papers and all of these other things, and internal documentation. And so to that end, there's a documentation team, some of whom work on code, but many of whom take what the developers have written in the code and explain it so that other people can actually use it. And then thousands of individual and corporate users. There's people who are installing this around the world and building it into products and using it in universities. And I'll talk a lot more about the university research later on. The whole project is led by a democratically elected core team of 9 members. I have served on that core team. I serve on that core team now. The core team does not set a specific technical direction. There is no central dictator to the FreeBSD project. The core team exists to make sure that everything goes smoothly. So if there are technical or personal issues between people on the project, they bring them to core, and then the core team tries to figure out how to come to a good agreement between those people. Core also often acts as a public face of the project, as does, lastly, the FreeBSD Foundation. So the FreeBSD project has no legal standing. It does not exist in terms of you ask a lawyer. The FreeBSD Foundation exists to help the project. We get financing for the project, and we interact with lawyers when we have to, because things that happen in the real world have to deal with law. So the foundation is the group that holds things like intellectual property rights for the project. And in this slide, I mentioned mentorship. One of the things that's really important to the project, when you've got a group of 300 volunteers and you're trying to get them to all produce something and work in one direction, if you think it's difficult to manage people who work for you, it's really difficult to manage volunteers. And so what's really important on the project is that we involve people in the project through a mentorship process. When people want to contribute to FreeBSD, first they'll join the mailing list, they might send some questions, eventually they'll send some patches. Eventually they'll send us enough patches that we'll get annoyed and decide that we should, what we call inflict a commit bit on them. So we should make them commit their own patches. But we don't simply turn on their commit bit. We give them commit access, but then we connect them with someone else in the community who's going to help them in terms of getting their code into the appropriate style. All of the code in FreeBSD follows a style guide called Style 9, which is named out of the manual page. Getting appropriate tests, getting appropriate interactions, and basically helping to integrate that new developer into the FreeBSD community. So mentorship is an incredibly important part of how the project works and how it's been able to survive for 20 years. So FreeBSD is one of the longest running, democratically run open source projects that's ever existed. Other projects may have lasted longer, but there are very few who've lasted as long as this. So I came here today to talk about FreeBSD and systems research. This is an area that's very interesting to me, and I think very interesting to everyone in the audience. So FreeBSD is a derivative of the Berkeley software distribution, which was started in the late 70s, early 1980s at the University of California at Berkeley. And CSRG, the Computer Systems Research Group that built the original BSD, built it as a research platform. One of the reasons that that work got funded by DARPA was so that there would be one platform on which everyone could do systems research and share their results, instead of everyone building a tiny little operating system specific to whatever hardware they happen to have in their basement. The idea was that with a single platform on which to integrate components and run tests and deploy systems, systems research itself could move forward much faster, and this is actually what came to pass. So starting in the late 70s, early 80s, a large number of fairly important bits of research were done on the early BSDs, including one of the first integrations of virtual memory into a large system, fast file system, which I'll talk about later, incredibly important for the development of the internet protocols, TCP/IP and the Sockets API. The Sockets API that everyone has used pretty much on every operating system since was developed first for BSD. Later on, Berkeley Packet Filter, and in all of the BSDs, the first versions of IPv6. So the versions of IPv6 that most people use today, developed by the Kame project in Japan. And here's one of the earliest references to a paper on the BSDs done by Ozel Poboglu and William Joy about the virtual memory system integrated into the original BSD. So BSD lasted for a large number of years, and the project finally ended in the 1990s, and then several projects were spawned off of that: BSD 386, OpenBSD, NetBSD, and FreeBSD, which is the one that I work on. In terms of FreeBSD and systems research, well, what's some of our motivations? Well, like the original BSDs, we really want a platform on which to build. We don't want to have to build up fake operating systems. For those who've taught classes or taken classes in operating systems, often they're taught on non-production operating systems that never will see the light of day in real products. They're only going to exist at your university or some small number of universities. But what we wanted was a platform on which we could not only do experiments, but which, if those experiments were successful, we could ship that code to other people, a large number of other people who would use it in deployed systems throughout the world. One of the things that's really helpful in systems research is to have a very large number of systems running your code, because you can't simulate the internet. You can try, but it's like boiling the ocean. And so it's much easier to just give your code to someone who's going to connect it to the internet and see what happens. So very strong emphasis on tools. The FreeBSD project really likes to build tools because we like to be able to make good statements about measurements. And we have a very strong commitment to measurement and to measuring results, presenting results, and then writing and sharing those results. So what makes a good platform for systems research? One of them is reality, and this is something I've been referring to in the last couple of slides, is that it's a real system that's executing on a lot of machines that people use. There aren't 10 of them, there are millions of them. Another is consistency. One of the things that you need for good software engineering, but also for good science, is a consistent platform on which to make your measurements. If the platform you're working on changes every week or every month, or even to some extent every year, and you can't find the previous system that you worked on, or it's very hard to track the previous system that you worked on, then as you're making measurements over time, it's very difficult to say something about the measurements you've made because they're not going to be comparable. Measurability, being able to measure what's going on, having a large amount of infrastructure in which to, having a large amount of infrastructure that allows you to measure the changes you've made, analysis tools, and finally, choice of open source license really matters. So I'm going to talk a little bit more about consistency. FreeBSD is very big on consistency. We believe in regular releases, and we believe in what I call KPI and API stability. And it's easier to show this as a graphic. So here's our current tree. I have a laser. Here's our current tree. And the way software is developed on FreeBSD is in the following way. You see this line going upwards. This is what we call the head of the tree. And the head of the tree is where all the new features go, all the new research goes. When people have some, hopefully not crazy idea, but sometimes we call them crazy ideas. But it's not so crazy that it can't go into the tree, then it's going to go into head first. And as we add features and as we add things to the system, eventually we come to the point of making a release. We try to make regular releases, and we hit them more often than not. So at some point we decided, okay, it's time to have release 9 of FreeBSD. And once we cut a release, that's called the stable branch. So now we have a branch in which no kernel APIs will change, the size of kernel structures will not change, and we will not change the programming API for users. So if you built an experiment on 9, anywhere on 9, it will always execute. Now, device drivers change, people change code, people fix bugs. So you may not get the exact same measurement along this entire branch, but you won't get wildly divergent results, and your code will not stop working. Your code will work for These branches last for 2 years of active development and then are kept around for 3 to 5 more years for security fixes. Companies that have integrated the code have actually remained on branches far longer. That presents some problems if they want to then eventually get to a newer branch, because this is a jump. So what we will not do between major releases is we will not preserve all KPIs. Now, we don't go higgledy-piggledy and just break them because we're that way. But in order for the operating system to advance, you have to be able to change APIs. You have to be able to add them, which is usually a problem. And we remove them occasionally. But it's when you change them or you change the contract between the program and the kernel or components of the kernel that you would get changes between major releases. So as the operating system advances, we move head forward. Eventually, the next major release will be 11.0 sometime next year. And then we will have an 11.0 stable branch, and we will deprecate the 9 branch. In order to keep our release engineering team from committing suicide, we try to reduce the number of major branches that we keep extant at any moment. That doesn't mean that other people can't keep them. Many people mirror our tree, and they hold on to branches much longer if they wish to do work. But in particular, if they're producing systems like appliances. So when people build an actual object and they ship that object, often they don't want to upgrade because they know what the hardware is and they know how to test it. But in terms of research, it's a little easier to follow this along. There's one more thing I want to mention. When people add new things into head, they are always candidates to be merged. So if that feature or that idea or that concept is one that can actually be moved back into a major branch without it disturbing the other components of that branch, new device drivers is a clear example of this. You have a device driver here, adding it back into an older branch isn't going to cause a major problem. But there are other things that we can add. People have added different file systems and support for other systems that were new and therefore didn't disturb the rest of the system. That's called a merge from current, MFC. So if you ever look at our source tree, you'll see commits called MFC. And what that just means is, oh, someone did something here that's really cool and useful. We'd really like it to be in 10 or 9 or some previous release. It's this commitment to regular releases, though, and to good software engineering that makes it a good, stable platform. For people who've worked on platforms that are less stable or looked at platforms that are less stable, you know how much trouble it would be if you ran a bunch of experiments and then 6 months later came back and all of your kernels were completely different. I said that the license was really important. I am not a lawyer. I get to say that every time I give one of these presentations. So the way I characterize our license is don't sue us. We would really like you, anyone, to use our code, and we really want to share what we've built, and we really want to share results. So in order to do that, we've created a license completely different from the GPL that has been used for many years now. It's been originally developed at the University of California at Berkeley, and it continues to shrink, which is kind of amusing. When the license was first written up by the University of California lawyers and the CSRG team, it had 4 different things, 4 clauses. It's now down to 2 clauses. I'll be very amused if I ever get our lawyer to simply just put "don't sue us," but I don't think that's going to work. So unlike a GPL-like license, which says that you must give back any modifications you make, the BSD license doesn't say that. In fact, it says you can do what you want. You don't have to give things back. And many people have pointed at that as a failing of the license because it means that we sometimes miss out on innovations that people have added based on our code, that people have extended our code or modified the kernel in such ways, and we don't get to share in that. But we believe that it's more important that more people run our code than that we get control of what other people have done. We look at it as saying that this is our code, this is what we've done, please use it. And if you would like to give things back, which many people do and many companies do, then we are willing to take them and we would like to work with you. But we are not going to force you to give us things. And because of this, research on FreeBSD can and does go into directly shipping code. And I'll talk about that in several examples. So I'm going to talk very broadly about 3 areas of research today and try to highlight some of the areas in which FreeBSD has been used very recently. Some of the papers I'm going to cite haven't been published yet. They They've been listed for their conferences, but they actually haven't been presented. 3 broad areas of research: file systems, networking, and security. Not that these are the only things that we do, but because when I was looking at all the work I wanted to talk about, they broke down naturally into these 3 areas. So the fast file system is kind of amazing. The fast file system was first developed in the early 1980s as part of the original BSD. The original paper on this is from 1984, and I graduated high school in 1985, so it's from before I even started programming operating systems. It is the longest-lived file system development project that I know of, certainly ongoing. It currently supports journaling, soft updates, snapshots. In fact, what's most interesting about the fast file system isn't just that the original design was a very good design, it's that it was an extensible design. In fact, I like to think of the fast file system as the project that launched 1,000 other file systems papers. And every time someone went and developed a new file system, like log-structured file systems, or they went and did journaling, or things like snapshots, McCusick and other people working on the fast file system would turn around and say, oh, that's a really great idea. I bet we can make that work in FFS. And they would just integrate that, and then there would be another paper. So it's been a really interesting platform for file systems research for 30 years, and it continues to be worked on today. Then it met its maker. So the fast file system is excellent for systems of gigabytes, but Sun Microsystems wanted to build very large zettabyte file systems, which is where the Z comes from in ZFS. This is now the big file system in FreeBSD. So this was originally done in OpenSolaris under a CDDL license, which is, I am not a lawyer again, a different license to BSD, but one that is not completely incompatible. So Sun built this system that can handle incredibly huge file systems and has become the place where people who want to work on big storage go to do their research. So things like RAID-Z, compression, and just seeing what you can store in massive file stores of terabytes, petabytes, huge amounts of data. That's currently done in ZFS. And at the moment, those are the 2 major file systems, and those are the 2 areas where almost all file systems research gets done from a systems research perspective on FreeBSD. Moving on to networking. So networking has always been one of the major areas in which the BSDs have excelled. Not the earliest implementation of TCP/IP, but the earliest widely shipped implementation of TCP/IP existed in the early BSDs and has continued to be updated, modified, and improved to this very day. It's also the component of the system that is most often lifted. So early Windows TCP/IP stacks were the Berkeley stack. The TCP/IP stack that exists in the embedded systems that currently wander around Mars, which I actually worked on, are all based on the early BSD stack. They took the code right out of it, and took it with the BSD license, and put it into the product. So it's an area where there's always been a lot of active research. And I'm sure people in this room know the work of Luigi Rizzo at University of Pisa. One of the earliest things he did in the FreeBSD stack was to add a system called DummyNet. And most people now think of DummyNet as a component of IPFW, which is used to do firewalling in the BSDs. But actually, it was originally intended as a way of evaluating TCP protocols, because if you didn't want to simulate the whole internet, it would be much easier to pass your flows through a machine that could do things like create delay lines or drop packets based on some algorithm, rearrange packets. So this is one of the earlier contributions from Luigi into FreeBSD, and this wound up as a SIGCOMM paper. Never one to sit still. I believe Luigi's actually given a talk here on NetMap. So NetMap is currently the big exciting thing for network and systems researchers using FreeBSD. It's also been ported to other open source operating systems, but it does not show up by default because it has not been accepted into their source tree. So when you install FreeBSD, you get this system called NetMap. And what NetMap does is it exposes hardware it exposes the queues and the rings from a NIC into hardware, allowing people to build incredibly fast and complex packet protocols on top of the operating system. And this supports a variety of hardware from Intel and Chelsea and others, 10 gig and 40 gig NICs. And using this, someone else who I'll talk about later has actually built networking applications that can completely fill a 10 gig pipe on commodity software and hardware. That's what we're going to talk about now. So some very recent, so recent that it will appear in about a week at SIGCOM, work by Ilias Marinos, Robert Watson, and Mark Hanley took the NetMap system and they thought, well, what can we build on top of this that would show how fast commodity hardware and software can actually run? And so they built Sandstorm and Namestorm. Sandstorm is a static content web server. Namestorm is a name server. They both sit on top of NetMap. And what they've been able to do is to show that you can use commodity 10 and 40 gig hardware to get 10 and 40 gig speeds with a commodity operating system if you have the right APIs. Right? And it turns out that NetMap for certain types of protocols is exactly the right API. In particular, if you want high bandwidth, it's definitely the right API, because what you need to do is to get directly at the hardware and to get everything else out of the way. Another interesting thing that's come out of their research, and if you look at the paper, which is currently online, you'll find that the performance of Linux and FreeBSD, which are compared to Sandstorm and Namestorm, have almost exactly the same curve. That is, they fall off in the same places and they increase in the same places. And there's a really interesting reason for this. A lot of people believe that if you replace all the lines of a piece of software, that software is going to operate differently. But it turns out if you replace all of the lines, but you keep the structures and the APIs the same, that software will operate in the same way. And so while the Linux stack was originally derived from the BSD stack and then completely rewritten, the fact that its data structures and APIs and how the cake is cut within the stack are almost the same means that the FreeBSD and the Linux stack operate almost the same now as they did 10, 15 years ago when the code was originally pulled in and branched. Some folks at Swinburne do a huge amount of really interesting TCP research. I actually feel they do interesting TCP research because Australia is so far from everywhere else, it's a really good test bed for long-distance networks. We used to have a saying at a company I worked at where we had colos in Australia, and the joke was, don't ping the Australia colos because every packet is 25 cents. So the folks at Swinburne have done some really great work around TCP in particular, and of interest to networking and systems researchers is Sifter. So what they did was they put a complete logging framework for interesting TCP changes in your TCP flows into the kernel. So the way most people do TCP research is they'll either create something in a simulator, or if they've got real traffic, they're looking at TCP dump style traces. TCP dump, another thing created in BSD. But what you're doing is you're looking at the packet traces without looking at the actual machinery as it runs. So Sifter puts in logging to the kernel that puts out interesting events as the state machine runs. So you can see things like, how are my congestion windows going? What are the scaling factors? What is the actual state of the finite state machine for TCP? What does each side of the connection think the smooth round trip time looks like? These are all really important if you're doing TCP research. And it's far easier to record it at the source in the sink and then deploy it than it is to try and get it back from a bunch of traces. So that's a bunch of the networking work that's been done. I want to talk a bit about tools at the moment. So one of the systems that was developed independently of FreeBSD, although happily with a BSD license, was LLVM. So most people now know about LLVM and Clang. This is a modern, extensible system for building compilers. Until LLVM came along, most people who were not using commercial development environments were using the GNU toolchain. If you've ever looked at the GNU toolchain and you've looked at the GNU compiler, then your eyes have bled. Because it was not meant to be extensible. As a matter of fact, it's specifically written against extensibility to prevent it from being to prevent it from being effectively reused in ways that its original author did not want it to be reused. So LLVM took a completely different approach. They wanted a modular toolkit for building compilers and running experiments on compilers and thinking about how they could do optimization and thinking about how they could learn about performance as the compiler ran. A really amazing system that they produced. A couple of things happened at the same time there. One was GPLv3, which was even more draconian than GPLv2, came out. And companies who wanted to ship compilers, like Apple, realized they needed a new compiler. And projects that want to be able to ship code that is not going to poison their downstream vendors or people who use it, like FreeBSD, also wanted the same thing. Luckily, Apple had money and we had hands. So Apple went and hired the entire LLVM team and then built a huge team around it and built that into their compiler. And the FreeBSD project adopted that compiler as the base compiler for FreeBSD itself. And this has had some really nice effects in terms of the kinds of research that's now being done on FreeBSD. So a couple of things were done both at Urbana-Champaign to look at how the compiler could be used to generate more secure systems. Coffee, which I'm told is pronounced just coffee, is a system built by these folks at Urbana-Champaign to lock out return-oriented programs, so to make it impossible for things that try to manipulate the system in a way that return-oriented programs do from running. That was done using LLVM to, that was done by using LLVM to implement the secure virtual architecture. And within SVA, if you look at the SVA papers, you can see how they use this to prevent ROPs from running. They chose FreeBSD because FreeBSD was already being built with LLVM, so they had an entire computing base that they could build with the compiler they wanted to use to prove that things were safe. So they used FreeBSD 9 because FreeBSD 9, while it didn't completely have LLVM for every architecture, was able to be built with Clang, the C language compiler from LLVM. They then went on and also did this thing called Virtual Ghost, which is a way of protecting applications from hostile operating systems by introducing a very small hardware layer generated by LLVM to prevent programs from getting at certain bits of memory. So these are two papers from 2014 that are all based on the work with LLVM and FreeBSD in combination. Virtualization. So FreeBSD was a little late to the virtualization game, in part because the way in which a lot of people use virtualization was to run, for instance, multiple copies of a web server. And you could already do that on FreeBSD with a system called jails. You could protect people from each other without creating an entire virtualization system. And so the drive for a virtualization system wasn't there, and if you wanted to run FreeBSD on a virtualization system, well, you could do that on anyone's. But eventually, a bunch of people at NetApp decided that they really needed a BSD licensed and also legacy-free hypervisor. And what I mean by legacy-free is that a lot of hypervisors have to deal with architectures on which there are not virtualization instructions. And the folks at NetApp said, we don't have to do that. We're only going to ever ship on modern hardware. All modern hardware has virtualization instructions and probably always will. So why don't we get rid of all of this legacy and do some new work? So with Bhyve, they created a virtualization system that can host many different operating systems, not just FreeBSD, in 10,000 lines of code, which is pretty small compared to what most virtualization systems require. So Bhyve is currently the virtualization system used by most people in pure FreeBSD environments. And turns out that doing this work has generated some interesting reuse cases, again, for research. One of the places where it's being reused is a system called OSV, which they call a virtualized operating system. This is to run JVM directly on top of a hypervisor, so that you don't have to run JVM on top of an operating system on top of a hypervisor. OSV leverages components of FreeBSD and also runs on Bhyve, as well as other virtualization technologies. the OSV folks realized there were a bunch of components they could get directly from FreeBSD, like ZFS and the network stack, and so they pulled those right out. So this is a paper that's going to show up in, that has already shown up in the 2014 Usenix ATC Annual Technical Conference. And that was done by a company, Claudia Systems. Other hypervisors, so FreeBSD also works with Zen, which was work contributed by Citrix that got DOM0 on x86 and ARM. And some of you may have heard of Hyper-V, I hope. So the FreeBSD project worked directly with the Hyper-V folks at Microsoft to make sure that FreeBSD ran well in Azure. So we got all of the drivers ported with them, and there are now images of FreeBSD available to you in the VM depot for Azure if you want to run that. Nothing about research would ever be done without talking about formal modeling. So there's currently two interesting products. There are currently two interesting projects that are utilizing formal modeling with FreeBSD. There's an effort currently underway at Cambridge to run FreeBSD on a system called L3. And L3 implements the MIPS ISA in a formal model. This has generated some very interesting results. For instance, we're finding, or they're finding, undefined behavior in the MIPS ISA, certain math operations that are really not well defined. It allows us to verify both the ISA and the operating system against each other. So this generates some very interesting discussions because most people are used to the idea of, well, is it my program or is it the kernel? Well, this is it the kernel or the formal model? You have to figure out if the formal model is broken. Another effort being undertaken both at UT Austin and also in Cambridge by Warren Hunt. The UT Austin folks have a complete formal model of the x86. So they can run x86 programs directly in a formal model and ask all kinds of interesting questions about the nature of the code being run under it. So they will eventually verify the entire trusted computing base on this simulated processor. The problem is that when all you have is a simulated processor, you need some other parts. Like if you want to run real programs, you kind of need a console. And you might need storage, and you might care about networking. But you certainly need a console, because just being able to load a program into a formal model doesn't mean that you can interact with it in any interesting way. So one of the places where the Bhyve work is going to show up in research is that parts of Bhyve are being reused in their formal model as the execution environment that acts the same way your system board would. And now we come to security. So there's been a long history of security on security research on BSD systems. The Capsicum work done in various places, but a lot of it has been done at the University of Cambridge, really brought capabilities back. Most people who had even heard about capabilities never believed they would see something that actually used them, because the belief has always been that capabilities are far too expensive and they aren't, going to be performant, and that systems that don't have capabilities are always going to be faster, and no one's ever going to do that. And there's currently a computer that was built for capabilities sitting in the hallway at the computer lab up at Cambridge, the Cap computer. But Capsicum changed this. So Capsicum was work done on FreeBSD, and it introduced lightweight capabilities for Unix and allowed the sandboxing of applications. So for instance, ping and TCP dump and procstat. And you might ask, well, who cares about sandboxing TCP dump? How dangerous could that possibly be? So one of the hacking competitions that takes place every year, the first thing people do is they try to send packets. Well, one set of people is trying to look at packets on the wire, and the other set of people are attacking those packet captures by sending packets they know will be able to root TCP dump, because TCP dump has to run as root. So if you know someone on your network is running TCP dump and you root TCP dump, then you have rooted their system. So it turns out programs that run as root and read packets from the wire, that's the first place you actually want to start doing some protection. Ping, TCP dump, procstat. And the Capsicum includes a set of APIs that extend the operating system so that you can do this fine-grained decomposition of programs. Some of the other work that's been done on top of FreeBSD because of the security features that exist in it is a recent set of papers from the folks at Harvard where they've created a scripting language not unlike a shell scripting language and actually intended to replace shell scripting languages called Shill. So this is built actually on top of the Mac framework. The components inside of Shill acquire and deal in capabilities and very likely will start using something like the Capsicum system in FreeBSD because it's already implemented on top of it to create a secure replacement for any one of the shell programs. And so things that people normally deal with, I mean, think about what shell programs do. Usually shell programs are doing things like running as root to install software on your system. Well, that's not a place where you'd want security, so it's probably not that important. It's incredibly important. So the components in Shill, like file objects when you open a file or you get a file, or sockets when you communicate with the network, or even environment variables, can be wrapped within capabilities. And that means that you have this way of, the shell programmer has a way of saying that only certain things need certain capabilities and only certain things will get them. They have a whole language for expressing this. And that's all based on work done at Harvard and then done using FreeBSD. So I mentioned capabilities and how people claim that they would be very slow, and there's all these problems with that. So one of the things that the folks at Cambridge decided to do is to start investigating modern boundaries in the hardware-software interface. And they've developed two systems, Berry and Cherry. Berry is a blue-spec implementation of the MIPS ISA, implemented as an FPGA, and it comes with an extended version of LLVM, which is all currently in FreeBSD. So if you get this hardware platform, you have a complete system for doing research on the hardware-software interface. You have an operating system, you have all the tools to work with that operating system, and you have an open-source piece of hardware that you can actually burn yourself with an FPGA burning kit or building kit in order to do your own experiments. And you can find that at Berry CPU. In terms of the capabilities work, Cherry can be thought of as a security extended version of Berry. So all of the things that make capabilities slow, the fact that they're not implemented in hardware, were then added to hardware. And so Cherry actually has support for capabilities in the instruction set architecture and the memory architecture. Again, like Berry, the platform and design are open source. So if someone now wants to do research on capabilities on a system where capabilities are actually built into the hardware, they have a complete open source platform for that as well. They've got the compiler and the operating system and the tools and the hardware. And all it requires is electricity and an FPGA. So I want to come to some of the more recent work in terms of thinking about how we're going to move forward with systems research on FreeBSD. And one of the biggest boons to this area, although I don't know that the original designers thought about this at the time, has been something called DTrace. So almost every version of any of the open source operating systems, and probably the closed source ones as well, have some form of tracing for debugging. But DTrace was really a major advance because it was a complete tracing system. It dealt with the kernel and user space. We imported it into FreeBSD 6 years ago now. John Burrell imported it. It's been consistently extended. There's a huge set of scripts. But what DTrace really gives us is, unlike systems where you have to hand add your trace points, it builds them automatically for you. The build process in FreeBSD will now build all of the trace points you want automatically. And so, for instance, every single system call and every single function call in the kernel or anything else you compile with DTrace turned on will be torn down and reassembled in a way that DTrace can understand. So this meant to the folks at Sun who built it that when they deployed systems, if there were some performance problems in the field, they could actually have someone go in and turn on a DTrace filter or a DTrace program and actually get information out. But what it means for the developer of an operating system or of a set of tools is, I don't have to think about what trace points I'm going to add. I don't have to add trace points for locking. I don't have to add trace points for many of the subsystems unless I want something very specific in the middle of a function. But if I don't need something very specific in the middle of a function, it's probably there already. It also gives a consistent measurement framework. I mean, if you look at the history of tracing systems and you look at things like strace and ktrace and all of the other systems that have ever been built for all of the other operating systems that have ever existed, they're all slightly different. And within the same operating system, you have a history of either updating them or changing them. So if you think of things, for instance, in FreeBSD, we have a system called Witness, which shows things about lock order reversals. Well, that was hand-coded. We have something that shows scheduler issues. That was hand-coded. Now we're going to stop hand-coding, right? I mean, we might hand-code a few small things, but we've got something that automatically generates that. Gives us this amazing visibility into all types of code. It can not only look at function calls or system calls, it can tear down data structures. So now I want to ask questions like Sifter asked about TCP. Well, I can get directly at the TCP data structure, and I can ask questions about it at runtime. It has built-in basic statistics. This is something that most systems researchers and most researchers really want. It's like, give me some statistical information on the data you've caught. And so the descripting language gives us that. It's extensible. Also, it's nearly free when not used. So when not in use, there are no instruction replacements. The way that DTrace works is at runtime, it will replace a single instruction where the function call was going to be called with a different function call. And so that introduces overhead. But you can ship a system with DTrace compiled in without paying even the cost of an if statement, which is the typical cost of most tracing systems. So what does it provide? Function boundary tracing, this is the 30,000 trace points in the kernel, which are just what the compiling system was able to rip out by looking at the function boundaries. System calls, a timing source called profile, so you can do things like build scripts that periodically look at things. Proc, IO, we've added NFS, and we're going to be adding a ton more providers. It's pretty easy to add them. And here's one of the ways in which we're going to apply this and how this comes back to systems research again. So Paolo mentioned at the beginning that one of the things I'm doing in Cambridge is helping Robert Watson develop a new master's course in operating systems at the University of Cambridge. And so what this course is going to do is it's going to use tracing as its method to teach students. So when I took operating systems a long time ago, we were given a toy operating system, shown a few things, and allowed to create ridiculously trivial device drivers. And if you've ever read a device driver for most operating systems, you'll realize that people who write device drivers don't actually understand how the rest of the kernel works anyway. So I don't know how that method was ever supposed to teach people operating systems, and I don't think it did. So the new method that we're going to try out is to actually show students complex data structures and interactions within the kernel at runtime using the tracing. And they'll be able to see things like locking and scheduling behavior without having to change the scheduler as their first attempt. They won't have to build their own system to figure out what is actually going on. They'll be able to look at complex TCP flows, and they'll be able to do real performance analysis with real experiments. So the lab experiments in the class will be using DTrace and performance analysis to actually show what happens when they make changes. So conclusion, FreeBSD, it's a platform for systems research. I mean, it's a system that's shipping in products, but it's also a system being used extensively by researchers to do this kind of work. Mature set of tools, low stress, business compatible license. And as you can see from the timeline, this is not everything that's ever been contributed, but it was some of the things I talked about today. Nearly 35 years of contributions to systems research. And everything you need is at freebsd.org. Any questions? Oops. Yes. Sorry, I can't really see people, so Paolo, if you can point at people. I've got the lights right on me.
Can you talk more about the measurement capabilities? Is it all in DTrace now, or?
So there are several tools used for the tape. The question is, can I talk more about measurement? There are several tools used to apply measurement to FreeBSD. DTrace is one of them, and I think DTrace, I'm currently working on DTrace, so of course I believe that DTrace will eventually be the centralized repository of all measurement. But in terms of doing things like performance analysis on instructions and caches at runtime, there's a system called HWPMC, which I also work with, which exposes chip-level performance counters to analysis tools. So if you're trying to collect a trace of how many instructions are executed between two places, that's done using something called PMC. Other performance tools generally work off the two of those, or people will do performance analysis or systems analysis using the exposed counters from every system. So there's no subsystem in FreeBSD that doesn't have a wealth of counters of what happened to the system, because we really believe in that kind of visibility. Yes, I can see, actually.
Someone has to ask, right?
Yeah.
Huge numbers of people still use Linux.
I don't know why.
Well, I was going to ask you, do you know why? What is missing from FreeBSD? What could you guys do to entice? I mean, it seems very important to you to have a large install base, right? A diverse one as well.
So there's a couple of answers to that question. So one of the reasons that if you look at the uptake of FreeBSD in Linux, you see Linux ahead, is that the BSD folks got into a bit of a lawyer discussion with AT&T, and so that delayed for several years the release of the source code. Although people could get a license to the BSD code, and this is before FreeBSD, for what to an institution would be a nominal fee of $1,000, but to an individual would be a huge amount of money. The code was not accessible to as many people as Linux was right out. So if you look at the graph, and Kirk, when he gives his history talk on this, shows this graph, you'll see that they're kind of following each other. As adoption goes up, they're almost straight lines. The other things I think that are missing are a lot of promotion. One of the things that we've talked about quite a bit is that the somewhat academic bent of the BSDs means that we are a little more reticent to just jump up and down and say, hey, we did this brand new thing. And as someone who is frequently brought up short by a colleague who will often say, oh, we did that in the Atlas in 1953, you realize there's nothing new, but you really should talk about it anyway. I think that's one of the places where we need to do a lot more promotion. Lastly, education. So one of the reasons to develop a master's course in FreeBSD is to actually get more students knowledgeable about it before they go out into the world. Right? A lot of people used the original Unix, and that's why Unix became part of a lot of products. And a lot of students have used Linux, and that's why Linux winds up in a lot of places, because you go to your first job, unless probably it's here, and and you say, oh, well, I've used Linux at school, I'm going to go use Linux somewhere else. So we think that promoting it to universities will actually have a really big boon to the operating system. Yes?
Do you not see it as potentially a problem for uptake that there are numerous BSDs now, which at least in terms of attention, they do compete with each other? I mean, at least from where I sit and
yes.
see it.
So as a FreeBSD person, I can say we have more installed base than any of them put together, but we all try to play nice with each other and not step on each other. We actually think that it's not a bad thing generally. So because there are different styles to each of the BSDs, the OpenBSD folks tend to be paranoid, is probably the nicest word. And so you get really interesting bits of security work out of them, right? So, we do some really good security work on FreeBSD, but there's a certain mindset that generates a certain interesting amount of work that we then will adopt. And one of the nice things that the BSDs have with each other is we have a pretty good working relationship. And stuff that's been developed or brought into one of the BSDs will go into the others. Certainly as a brand identity, I would say that there's an issue there, but I'm also not a marketing person. Other questions? Yep, well, sure. You can ask another one.
With the focus on documentation, I wonder whether you end up in the situation where there are actual code changes which are driven for the desire for better documentation, or whether the influence only goes the other way. You only change the documentation based on the code.
So that depends on your point of view. Certainly from the standpoint of applications that run in user space. So one of the main tenets of the FreeBSD project is the principle of least astonishment. So if someone builds a piece of code that's really cool, but yet when you use it astonishes you, not in a good way, often we will go back, the documentation team will usually be the people who figure that out because they'll actually try all this stuff. and they interact with users a bit more than, say, a deep kernel developer will. And they'll say, well, that's really cool, but could you make it so that when you run it, it doesn't make people's eyes bleed? And so you will get changes that go both directions. I'd say the majority is pretty typical for software, where a lot of the changes in documentation are driven by code. But it does go both ways. And the documentation team has license to tell people to, fix things and make them understandable, because they're really the ones who are interacting a lot more with less deeply technical coders. Other questions? Yes, all in the back.
I was curious about the LLVM part. So now the whole system, including all the libraries, like C library, everything is built with Clang, right?
Yes. So everything is built. The question is everything built with Clang? And yes, everything is built with Clang.
Okay. Is it possible, do you know if this is possible also to emit LLVM bit code on the side, except for, building it for x86 or x86-64?
Yes, that's also possible.
No, the code will do it automatically. Isn't in the base system, but it's on GitHub, and if somebody wanted it, we could easily commit it.
Okay.
Brooks here works on some of that, so that's why I was looking at him, because I sort of knew the answer, but I was waiting for the nod. Other questions? All right. Yes.
How long do your tools take to build the entire system?
How powerful a computer do you have? And if you're building on a typical modern multi-core machine and you want to build all of world and all of the kernel, it's an hour and 15, depending on how fast your machine is.
It's better than a week anyway.
Yes, it does not take a week.
My builds are 15 minutes.
He has a really good machine. I often cross-build from a laptop, so it's a little slower. But yeah, it's pretty fast.
That's not all 24,000 ports, is it?
That is not all 24,000 ports. That's all of the user space and all of the kernel. The ports take about a day. Yeah, a little less than a day for everything to be built, because everything can be built in parallel, and we run on 64 core machines, and I think we're about to run on 128 core machines, and we'll just throw a lot of cores at it. All right. Well, thank you very much.